Okay, so this chapter is all about a very important one, the inverse of a quadratic, and I urge you to learn it. I also urge you to learn it for something more complicated, like a rational. So let's give the worst case scenario here. Squared plus 4, and we'll put even a 2 in here, like this, and all of it squared. Now your first step will be to replace the f of x with a y, like that. And your next step will be to swap wherever you see an x, put in the y, and wherever you see the y, put in an x. Let's just do this here. So wherever I see the x, I'm going to put in a y. So I'm going to switch this over there, and I'm going to switch this over there. And now the whole point is to identify, or isolate rather, this y. But if ever you have trouble undoing an equation, I want you to use this method until you get good at reversing it. Because undoing an equation is essentially just reversing bed mass. And bed mass simply says brackets first, then exponents, then division and multiplication, then addition, subtraction. And undoing it is the reverse of that. So if we were to tell this story in bed mass order, I can see some brackets right here. And yeah, there's 2 brackets, but you're essentially moving from inside where you see the thing you're trying to isolate and what's happening immediately around it. And if you're going to undo it, you're undoing from the outside in. But if I can see a bracket here. So that's the first thing I'd have to focus on, the bracket. So what's happening in the bracket? 1 is being subtracted. And then if I go outside the bracket, I can see that we're still inside this bracket here. This 2 comes inside the bracket before the exponent. So I'm still inside a bracket. And I would say, okay, after I subtract 1 from y, it is being multiplied, y is being multiplied by 2. And finally, I'm outside the bracket, and I can see now I'm dealing with an exponent before the 3, because we're going in bed mass order. And the exponent is, it is squared. And you can number all these things, by the way. And after the exponent, I can skip. There's no more brackets. There's no more exponents. There's just this multiplier. You might have said, how come that multiplier came before this exponent? Because it was inside this bracket. Okay, so now we've done we've gone all this bracket. So now there's only one multiplier left. It is multiplied by 3. And finally 4 is added to it. The very last thing outside. And you can number them. So it's 1, 2, 3, 4, 5 things happen there. Okay? Now you're going to reverse the story starting with number 5 and reverse the action. So number 1 of how to undo this, what's the opposite of adding 4 to it? Subtract 4. Number 4 story, what's the reverse of multiplied by, I think it should have said 3. Multiplied by 3. What's the reverse? Divide everything. Divide both sides by 3. Number 3, what's the reverse of number 3? Of squared. Square root both sides. Number 4, what's the reverse of number 2? It's being multiplied by 2. You can either divide by 2, as I did, although keep in mind I like multiplying by the fraction, the reciprocal 1/2. I prefer that. Both are the same. 1 you're going to find easier. And finally, what's the, oh, that should have been 1, 2, 3, 4 here. 4. And finally, what's the last step that we're going to have? It's going to be the reverse of number 1, which is add 1 to both sides. Now you have a formula or a method to undo this thing, and you can use it in order. So the first thing we're going to do, we're going to subtract 4 from both sides. And you're going to get used to the idea that, you're going to get used to the idea that you can just start with this step and go in reverse BEDMAS order once you get faster and faster. So I'm going to subtract 4 from both sides. Now once you have a 4 subtraction on the other side with x, I strongly encourage you to put it in brackets. Like that. And what happens when I subtract 4 from the right side? It disappears. That's the whole point. So that's that step. 1 is down. Divide both sides by 3. So I'm going to use, I'm going to divide by 3. So that means I divide the right and the left. And as long as you're doing both sides of an equation the same thing, you are not messing up the equation. So I'm going to divide it by 3, gets rid of that. What's my next step? Square root both sides. Now here's the little trick of square root. I'm square rooting this side to get rid of this. But when I square root anything like that, I must add a plus or minus symbol. It's just the nature of it. When you square root 4, if I take a square root of 4, the actual answer is plus 2 and minus 2. And that's because minus 2 squared is 4, plus 2 squared. Minus of this squared will achieve this, and plus version of this squared will achieve that. Okay, what does it do on the right side? It gets rid of the square. Right? That's what a square root does. If something was cubed, you would cube root it. So that's number 3 done. And then finally, number 4 says divide both sides by 2, by half. Now here's where I prefer multiplying. We've essentially broken through to this bracket now, because we got rid of the square. So here's where I actually prefer to multiply both sides by 1/2. So I'm going to multiply by 1/2, which is the same as dividing by 2. When you multiply, and when you want to get rid of a number and you multiply it by its reciprocal, you'll get rid of it. But I can see I must multiply this other side by 1/2, and it doesn't matter if I put the plus minus outside of this, like that. And that essentially gets rid of my 2 and my brackets. And finally, I must add 1 to both sides. So I must add 1 to both sides. When I add 1 to this side, it disappears. And when I add 1 to the other side, this is what I get. Notice that the reciprocal of a quadratic will always be a square root function. And you'd be tempted to think it's going to look like this, like a square root function. But that minus also includes the bottom half. So keep that in mind. That plus minus keeps both halves, and a square root function is only 1/2. So this suddenly, now when I'm done with the y, and I replace it with this. And to show that it's an inverse, we use this little symbol here. We put above the f -1. And that shows that this is the inverse equation of the f of x equation there. The other thing you'll discover about the inverse is look carefully at it. Everything in here is happening in there in inverse, from inside out, right? So let's outside in. Let's look at the 4. Well, the x is being subtracted by 4. Let's look at the 3. Well, that whole thing's divided by 3. Then we got the square. Well, the whole thing's square rooted. Then we've got multiplying by 2. Well, the whole thing's being divided by 2. Then we've got 4 added to it. Well, the whole thing. Oh, did I subtract 1 by mistake? Nope. Yeah, then we've got 1 subtracted from it. Well, the whole thing adds 1. So everything affecting the x here is now affecting the y in an inverse order, like the reverse of it. And everything that was affecting the y is now affecting the x in the inverse order. And once you get used to that, you can just look at that and write that. Get very fast at it. But you can use my method first when you're slow at it. Then when you get faster, you can automatically just reverse BEDMAS. So reverse BEDMAS, subtract 4, divide by 3, square root it, divide by 2, add 1. So I'm going from outside the bracket inwards. And then when you get really fast at it, you can just automatically say these are y transformations, so they're going to become x transformations. And the inverse operation, and these are x transformations, and they're going to become y transformations in the inverse operation. And that's because when you're switching x and y, the domain and the range switch, and all the x and y values will swap. So you have to have a consistency. So obviously it's just going to be an inverse of all the transformations. Keep that in mind. If you have x and y values, just swap them, and you will find the new inverse graph. And if I was to plot this, we will find inverse points here and here. But I'm going to go on. And actually, yeah, if you have time, it's smart to go ahead and experiment with Desmos. And I think it was, I can't remember if it was 3, 2, x minus 1 squared plus 4. Was that it? Get rid of that. It was minus 1 and 2 beside it. Yep, like that. So that's that. Notice it's vertex is right there, 1, comma 4. And then the inverse, and I believe Desmos can even do, if you want to do learn how to do a quick inverse, this is a good tip. You can take the same equation, make it g of x, or make it y and x, and then when you see y, just put x, and when you see x, just put y, and it'll instantly draw it for you, which makes sense. We're swapping x and y's. But also, if you were going to do the inverse formula that we did, g of x is equal to, let's see, it was a half times, and I can't do the plus minus on this one, square root of, it was x minus 4 divided by, and I got to put it, yeah, it's going to be divided by, in brackets here, 2, and let's see, I got to get this right. It was half x minus 4 divided by 3. Okay, oh, did I get that right? Oh, let's see. I subtract 4 divided by 3, yep. And then the whole thing has a added 1 to it. Now notice these, oh, I missed something. It's not x minus 4 over 3 square root plus 1 minus 4 divided by 3 square root, the whole thing divided by 2, which is multiplying by half, and then add 1. Whole thing set square root. Oh, here's what's going on. No. Oh, it's plus 1. It's plus 1. And plus 4. Is that right? No, it's minus 1 and plus 4. So let's see what I got wrong here. Did I do the actual thing wrong? Half x minus 4 divided by 3 square root times a half plus 1. That should have worked. I'm really puzzled why this is not working. No, there's no reason for that not to work. Three, two, one, 4. Ah, right there. There we go. And that means this is not there. Doesn't take much. And now they match. Desmos is not good at putting the minus here, so you have to put one with the minus and make it green as well so you don't confuse yourself. And there, I've successfully done it. You can see it matches the blue. Now, it doesn't take much to screw that up. And yeah, I'm going to continue. This is an obvious question. I'm not going to get to it. And they just teach you how to undo things. We're going to go right to the questions because I wasted so much time there. Always look at your summary at the end. And here we go. So for inversing ordered pairs, you can just swap them. So you just swap them. It's going to be 0, 0. It's going to be 3, 1. It's going to be 12, 2. And it's going to be 27, 3. By the way, inverses also reflect through the y is equal to x line, which makes sense because we're swapping x and y. And if I look here, 4, 1, it'll be the inverse of the vertex there. And I can even find a point here. Let's say if there's a clean point somewhere. Looks like there's going to be a clean point somewhere there. 7, 0.5. So I'm going to find a 0.5, 7 over here. So you'll always find their swap points. And since you're swapping x and y, it makes sense. I'm not going to do the next one. It's pretty obvious it's the same thing. And notice that the inverse of a parabola is not a function anymore. Given the graph the inverse. Okay, so for this one you'd find some points. So we know we're going to have this share point here. And always use clean points. So here's 2, 4 right there. So we're going to use 4, 2. And I can tell you, well, right over there, we're going to get minus 2, 4. So we're going to get 4, minus 2. And you can graph some more points if you want. Just essentially swap them. And there you go. And that'll be your inverse. It'll be a little bit squishier like that. And they'll share some points sometimes. If you'll see them share a point where something swaps the same, or just by chance. For instance, there's a shared point right there, 1, 1. And what about this one? So this point here, this vertex here is minus 2, 3. So we're going to get 3, minus 2, which is right there. This point here is minus 3, 0. So we're going to get 0, minus 3. So 0, minus 3 is down there. And this point here is minus 1, 0. So we're going to get 0, minus 1, like that. And you can do another point if you want. Looks like there's a clean point here. So it's 0, minus 8, which means minus 8, 0. And the other clean point will be over here. It's not quite clean, actually, now that I look at it. So you should choose clean points. It looks like minus 9, 0 is the clean point. So I get minus 4, minus 9. So minus 9, minus 4, somewhere around there. And then I just get this. So I can even put it right through there. And there we go. Notice if I draw a line y is equal to x, which goes evenly diagonally through any graph like that, we will see a sort of reflection. This point reflects over there. This point reflects over there. This point reflects over there. And they'll always be equidistant, even when they cross over. They'll be equidistant to the other side of the line. Given this, determine the equation of the inverse. So we'll see if we follow the correct steps. So first, replace everything with y and x. Make it a bit bigger. 2x squared minus 1. We're going to swap our y and our x right now, and then I can't forget to put the squared. And now I'm just going to reverse bedmass this. So normally it's squared. The order will be squared multiplied by 2 minus 1. So I'm going to reverse bedmass. I'm going to add 1 to both sides. And put the x plus 1 in brackets. The right side, it disappears. So I'm left with this. I'm going to divide by 2 on both sides. The 2 on the right is going to disappear, and it's going to go over here as a divider. And then finally, I'm going to take a square root of both sides to get rid of this square, and I'm left with y is equal to the square root. But when I square root, never forget I have to add a plus and a minus. And you can always put that in bedmass or in Desmos. But you can also see, for instance, when x is 1 in this one, y, actually let's take x is 3. 3 squared is 9. 18 minus 1 is 17. When I take 3 as x in here, I get 3 plus 1, 4. Let's see. Sorry, I got to take 17 as the x in here. 17 plus 1 is 18. Divided by 2 is 9. Plus minus square root of 2. So I get the point. 17 comma 3 and 17 comma minus 3. And so you can see when I put this point in here for x, it will spit out the y. So the x's and the y's have swapped. And that's how you know you did the correct inverse. Practicing. Okay. So, what's this first one mean? It says just put it 3 in there and find it. 3 for x, minus 1 is 2. 2 squared, 4. 4 times minus 2 is minus 4. Oh, sorry. 3 minus 1, 2. 2 squared is 4. 2 times minus 2 is minus 8. 7 minus 8 is minus 1. So that means the result of this is minus 1. Then they want us to find, this means find the inverse of this formula. And then they should have actually done minus 1 to show us that we get back to 3. But we'll do the inverse of this formula. And we're going to first say, okay, notice there's a little restriction here. I don't know why they put the restriction. But our first step is to replace it with y. And then even our second step is to move the x over here. And the y over there. Doesn't really matter. If I have I'll type in the y. Like that. There we go. Now, notice it's not quite in the correct order. This is essentially being added to it, even though the other one's subtracted. So in reverse bedmass order, it would be that one first, then the square, then minus 1. So I'll show you what I'm going to do to the left side. I'm going to subtract 7 from both sides. And I'm going to put it in brackets. When I subtract 7 from the right side, this 7 disappears. I'm going to divide both sides by 2. And when I divide the right side by 2, minus 2, obviously those minus 2's will cancel out. Then I'm going to square root both sides to get rid of the brackets. But when I square root, I must add plus and minus. And then finally, I'm going to add 1 to both sides so that y is equal to this whole thing plus 1. I want you to notice that all the x transformations, let's bring back the original equation. And this is the new equation. Oh, and then replace this with this. Now I want you to notice that all the x transformations here are now, oh, you know what? Let's see. subtract 7, divide by minus 2, square root it. Yeah. So this looks like it's an x transformation, but it's not in with the square root. So it's actually a y transformation, especially when I rephrased it, right? And that's why it's now an x transformation. This was a y transformation of plus 7. That's now why it's now an x transformation. And these were this was the only x transformation right there, which is why it's the only y transformation down here. So just be careful when you do it the shortcut way. For this to be an x transformation, it would have had to have been in the brackets and squared outside. So now if I'm going to solve this, I just put 5 into the inverse. 5 minus 7 is minus 2, divided by minus 2 is plus 1. Square root of plus 1 is 1. So we get plus or minus 1 plus 1, which means, what does that mean exactly? It means we take 1 that's plus 1, which is equal to 2, and 1 we take that's minus 1 plus 1, which is equal to 0, which means that f of 5 produces two values, one that is 5, 2, and one that is 5, 0, which makes sense. If we were to graph that, we would see why that makes sense. And then finally, what do we do for this last one? Well, you're going to learn in functions, the reason we've learned this notation is you can put anything you want in for x, which means if I enlarge this a bit, wherever I see x, I'm going to put, I have to sort of make a special bracket, I'm going to put this. So what happens immediately? I can see that the 7s disappear. I can see that the 2's divide out by each other. Now here's the only problem. I'm left with a minus a. And a minus a in there, if that was intentional, cannot be square rooted. So that would instantly be it cannot be done. However, if it had come out as plus, then the answer would be this. But because it came out as minus, well, I mean, if a is a minus value, though, this is still a legit answer, because you could substitute minus 1 for a, and it will still work. So this would be your final answer. It will be the square root of minus a, plus or minus square root of minus a plus 1. And you might say, well, you can't have a square root of a negative number, but that's not a number. So if a was equal to minus 1, this would become plus 1, which is resolvable. So you just go as far as resolving it as possible. Okay, what about the other ones? Let's see. So you can see this is going to take a while. I'm only going to do a few at a time and probably take a break in between. Sketch the graph. Okay, so before we sketch just means don't go crazy with it. And I can see the vertex is 2, minus 2, and I can tell you the inverse will be minus 2, 2. So I'm going to, in red right away, put the vertex of the inverse. And I'm going to try to graph this close. So 2, minus 2 is roughly here. And minus 2, 2. I should make that first one in green. And minus 2, 2 is roughly here. And then if I want a couple of other points, just take, since this is 2, I know this is the vertex of this. Just take a point just to the right of that. So take 3. 3 minus 2 is 1. 1 squared is 1. 1 times 3 is 3 minus 2. So I get 1, 1. And then take, 3, 1 I took. And now take x is 1. So 1 minus 1 is minus 1 squared is 1 times 3 is 3. So I get 1, 1. And now in green, I can plot these. So I get 3, 1 up here and 1, 1. And automatically I can say in red the reverse is going to be true. I'm now also going to have the points down here. 1, 1, so we're going to share that. And 3, 1. So we're going to share this point. Oh, sorry, that's not 3 comma 1. It's going to be the inverse of it, 1 comma 3. 1 comma 3, which is up here. And I already know the first one's a parabola. So it's going to look like this. Roughly. And I also know the other one's a sideways parabola. So it's going to look like this. Roughly. And there's going to be a nice symmetry. Notice they form a nice heart through the y is equal to x line, even though I just sort of sketched this. But boy, that I got it pretty bang on. You can see that nice heart on either side of the black line. And all you needed was 2 points on just near the vertex. I took one more than the vertex and one less than the vertex to get these nice symmetrical points. And then I could just reverse it to sketch it. I didn't even have to inverse this formula. But if I am going to inverse that formula very quickly, it's going to be this. So the inverse of that, f of minus 1x, is going to be, I know it's always going to come out as a square root, plus or minus. And I know it's going to be x plus 2 divided by 3, and then plus 2. That was a y transformation. That was a y transformation. That was an x transformation. That will produce the same graph. You can use the methods I used before. I'm just showing you that it can be done quickly. Graph this. So this is a square root function. So if I look at this, my knowledge of the square root function, it goes through these points. 0, 0, 1, 1, 4, 2. Like this. However, this minus multiplies all my y values by minus, which means it's actually going to go down to here. And the points down here will be 0, 0, minus 1, 1, and, or sorry, that other one's 1, minus 1, and the other one's going to be 4, minus 2. Essentially, all my y values became a negative number. Graph its inverse. Well, I just have to swap its numbers. Now, what's interesting about the inverse of a root function is you'd think it'd become a parabola, but no, it's going to become half a parabola. So I swap these points. They're going to share 0, 0. This is going to become minus 1, 1. So minus 1, 1. Oh, I got on the wrong side even. It's over here. And minus 2, 4 is over here. And then if I sort of join them, it's something like that, even though that's messy. Like that. And that's all I had to do. I didn't even have to come up with it. However, if I am going to come up with the inverse of this, oh, what's the domain and range here? It's x in red. X is bigger or equal to 0. Y is smaller or equal to 0 because it reflected in the x-axis. Now, for this, I just swap their domains and range. For this one over here, in green, the domain is going to be x is smaller or equal to 0, and y is smaller or equal, or sorry, y is bigger or equal to 0. So notice this domain became this range, and this range became this domain. And it matches the graph. State the domain, determine the equation. So how would we inverse this equation? How would we inverse that equation? Okay, so square root is treated like an exponent because it's x to the half. So that's the first in the bed mass order, and that's last. That's the next thing. So to reverse it, first of all, we're going to make this y. Then we're going to swap the x's and the y's. So this is going to become x. And this is going to become y. And we're going to first divide by minus a half. And if you get confused why, tell the story in BEDMAS order. We're square rooting first, then multiplying by minus 1. So we should divide both sides by minus 1, then square both sides. So when I divide this by minus 1, cancels, and over here it just becomes minus x. It disappears. And then I square this. So I get a weird parabola that is flipped. However, you'd be tempted to draw it like a parabola, but the domain and range must be restricted. So you must suddenly say x must be smaller or equal to 0. So even though, and I'll show it to you, it's clear with BEDMAS, or it's clear with Desmos, if I swap and just make that y is equal to, and then just swap their x and y's, you can see it's the half parabola. I did it. If I use the actual equation we just came up with, you can see it creates both parabolas, and that's not what we want. So that means you have to restrict this formula in the same, you have to figure out the domain and restrict it in order for this formula to achieve the actual inverse you're looking for. Because this right side of this red line, or this top side, does not exist. Therefore, it cannot exist in the inverse, even though in the formula, without this restriction, suddenly it's a parabola. But it cannot exist. It must be the exact inverse of what you're looking for. Then they go on, and I'm going to have to take a break, and I'll be back. Okay, I'm just going to continue a couple questions. Might have to take a break. You'll find that a lot of them are the same methods over and over again. Determine the equation for the inverse of this. So if we look, this is going to be a quadratic, and they only want us to consider for x above minus 1. So they only want us to consider the right side of this. And if you look at the vertex, you can see it right there. The vertex is minus 1, comma minus 3. Since we're only considering for x bigger than minus 1, which is the vertex, and then the vertex is roughly there, we're only going to be interested in this side of the graph. So obviously when we're doing inverses, they're looking for inverses that will look like half of a root function, which is probably something I might have missed earlier. So for instance, I think there was another one where they limited the domain. So if I look at this one, I can see that this is reflected in the x-axis, so it's facing down. It's translated 1 to the left and translated 3 down. So if I were to just take the 3 standard points for a quadratic, which would be this, or even this, we'll do minus 1, comma 1, and I just say, okay, well, I'm going to translate, I'm going to multiply all the y values by negative, and then I'm going to subtract 3 from them. And then I'm just going to subtract 1 from all the x values. So this one's going to be out, but this one's going to be the new vertex. And this is going to be in, and this is going to be in. So I can just ignore this one. And then I have 3 convenient spots right there. So it'll be here, going facing down here, and then it'll be like that. It'll be something like this. And then to plot the inverse, they want me to figure out the equation, but I can grab some inverse plot points right here. The inverse of this will be minus 1, minus 3, comma, minus 1, minus 4, comma, 0, and minus 7, comma, 1. So I can immediately say, okay, well, minus 3, minus 1 here, probably more like here, minus 4, comma, 0 here, and minus 7, comma, 1 here. So it's going to be like that. You can see normally this would be downward facing, and this one would be a sideways facing like that. But we're only going to be concerned with this part because the range will become the same as the domain of this. So y is bigger or equal to minus 1, so over here. And then if I look at the domain of this, or the range of this red one, it's y is smaller or equal to 1. So up here it'll be x is smaller or equal to minus 1 rather. Let's see, let's make sure minus 3 rather. So over here it'll be x will be smaller or equal to minus 3, which makes sense because the vertex is right there. So to rehash, both the domains and ranges will flip. The domain and range of this red one is already given. The domain is given as x is bigger or equal to minus 1. And when we look at the vertex, it's y is smaller or equal to minus 3, which means the purple domain of this will just be the reverse. X will be smaller or equal to minus 3, and y will be bigger or equal to minus 1. And graphing it, we can see that's true. If we're going to come up with the inverse formula, though, I'm going to take this. I'm going to just get rid of the graph, so you get the idea. And I'm going to swap the x and the y, so the x will come out, and inside I'll be left with the y. And I'm going to try to isolate the y, and don't forget there'll be an equal sign here. So if I quickly look, I'm going to add 3 to both sides. And that'll get rid of this. Then I'm going to divide it by negative 1, which essentially just puts a negative in front. And that gets rid of that. Then I'm going to square root it. And normally I would add a plus and a minus. But in this case, we're not going to be creating both sides of it. And we'll have to wait and see which version we're using. So that gets rid of the squared. And then the whole thing is subtract 1. The whole thing is subtract 1, which means the f inverse of this is equal to this on the left. And I can see when I put negative 1 in here, this becomes 2, and then negative, so I have to put negative 3 in here. This becomes 0 and 0. Negative 4, it becomes negative 1, which becomes positive 1. And that's why the domain will be that way. And since I'm looking for results of this, that'll only be y is bigger or equal to minus 1. That means I do not want to put a negative in front. It's just the positive version. You get more used to that as you go. You'll see each of these questions are the same. Given this function, find the equation for the reverse, and it's for the part of the function where x is smaller or equal to 5. So essentially they're taking the vertex, and which is 5 comma 3. And just to confirm, because I've cut off some things, so I think for the inverse they're restricting the domain, which is odd. I think no, it's got to be for the original. So if I look at the domain, the vertex of the original, it's that. And use a graphing calculator for the inverse. So I'll just work on, show you how to come up with the inverse very quickly. So if this was the x and the internal was the y, right? If this was the y in there, it would become x minus 3. All of it times 2 to get rid of that half. then it would be square root, and then I would add 5. So this would be it. And since we're talking about x only for smaller or equal to 5, and this is an upward facing parabola normally at 5, 3, we would only be talking about the left side, which means when I inverse it, I believe we're talking about the bottom side, but we'll see. Yeah, because then y must be smaller or equal to 5, and the new vertex on this new one is the inverse of that, 3, 5 down here, which means if I'm making it y smaller or equal to 5, it's going to be the bottom half of it. So what we're going to do is I'm going to graph calculator, use Desmos. So there's the original, but keep in mind they only want us to use the left side. And the inverse, since I'm going to use the new version of it, it's going to be x minus 3 times 2. All of it will be square root, so I'll just put this in there. And then minus plus 5, rather. Nope, without the square root. Like that. And however, I've restricted it the other way. So in this one, I'm taking it the negative version. And why is it negative? Because if x is smaller or equal to 5 in the first one, that means in this one, I have to do y is smaller or equal to 5. And that will restrict, and yeah, it's not going to let me do it, unless I put it like that. And that would restrict it. If I had it plus, for instance, it's not going to show me anything. So that proves that it should be this bottom half. Because if I did include that restriction, I'd get a full side parabola. So just keep in mind, whatever domain restriction they put on the main one becomes the range restriction on the inverse. So the blue one is that. Notice they accidentally share this point because those points are equal to one another. So when you swap their x and y's, they become the same value. They also share this point accidentally and this point accidentally. So turning off the red one, that's the inverse, and that's the left side of the parabola. If I get rid of the domain restriction, that would be it, and the inverse would actually be this. Like that. Moving on. So for this, so we're very specific between minus 2 and 3. We should factor this correctly first. You can see that that's in standard form, and you cannot find the inverse. You cannot find the inverse for that. We could find the extremes by plugging in minus 2 and 3. But we're going, and actually that would be a good way of doing it, but let's try some factoring first. So this means I have 2 points in here, 0, 0, and 2, 0, which fit within the domain, which means the axis of symmetry is at x is equal to 1. When I put x is equal to 1 in here, I get 3 minus 6, so it's minus 3. Which means my most likely equation for this, if I were to complete the square, would be this. However, what I'm going to do is, and then you'd have a little square here, what I'm going to do is actually complete the square to determine if I get that formula. Also notice the range restriction, so if I put minus 2 in here, I get 4 times 3, 12, and minus 2 here becomes plus 12, so I get minus 2, 24. And if I put 3 in here, I get 9 times 3, 27, minus 18. So I get 3 comma minus, sorry, comma 18, because it comes 27 minus 18, sorry, 3 comma 9. And so it looks like the range goes between 24 and 9, which makes sense because the vertex is right here at 1 comma minus 3. It's upward facing, so it's going to go up like that, but obviously it reaches a higher point, so it would appear the range is this. But we'll confirm that. They already gave us the domain, so that's kind of weird that they would ask us the domain. But let's first complete the square. Our first step is to factor out a 3 out of there. We get x squared minus 2x. Then the perfect square of that is 3x minus 1. And I know I'll be subtracting a 1, and when I multiply by 3, it becomes that. And sure enough, that is what happens when I complete the square. I'll keep these. I don't need those anymore. And if I quickly find the inverse, this is the inverse. That becomes that, that becomes that, and that becomes that. However, its range must be restricted in the exact same manner. So now its range must be restricted like this. So you must determine the min-max values that can possibly exist. Now I believe, since we found this, we will determine, probably most likely determine that that is the domain. But I'm going to let Desmos do it for me. Or sorry, yeah, the domain. And I also want to show you what the proper writing of this is to determine the stretches. It's actually a third in front. And then you'll have x plus 3 in the bracket. So that third will tell you, okay, this is a root function that's stretched by horizontally stretched by a factor of 3, translated 3 to the right and 1 upwards. And that'll allow you to graph it easily too. But we're going to put this one in all its formats. Okay, let's see, the confirmed at the vertex is 1 comma minus 3. Let's put the restrictions, the very strange restrictions. And we'll see if that's indeed the restrictions. Yep. Oh, I had it backwards. There we go. Let's see if that indeed reflected the range. Yeah, so the range goes from 24 all the way from minus 3, and we'll see if that's indeed the domain of when we flip it. Now, I'm going to write it in this format so that we can see that it's the same thing. So there we go, we've got the same graph. And then I'm going to just swap the x's and y's to show you the inverse. But now I'm also going to put this as a restriction on the y to see if we get the same x's. Now, there's the lowest value of x. So I said that it would be from minus 3 to 24. And sure enough, look at that. The restrictions on the, get rid of this one, the restrictions on the red for the domain are the same as the range restrictions on the purple, and the restrictions on the domain are the same as the range of the purple. To figure out the range of the purple, you had to figure out the highest value of y would be, and you had to figure out that the vertex is the lowest value of y in order to deduce what the domain would be on the red graph. And to do that, you'd plug in your values that you're given. And you'd know the furthest left or the furthest right from the vertex is going to give you your highest y values. And just to show you the correct version, so we got x, and it was x plus 3, all divided by 3, I think. And then it was plus 1 outside the square root. And there we go, and we just have to put the same range restrictions that the domain had before. Or same domain restrictions, rather. Here we go. And let's see if we got it. Oh yeah, because it's done the top side. I believe we have to do the negative side. I should have tested that out as well. There we go. Let's see if I get the same. Almost. It's got to be minus 3 here. There we go. I think I got the same. Oh, I can't just put minus. Yeah, because Desmos will only let me do one side of this. And if I remove it, it's doing the wrong side. So I've got to kind of do it for there. It's really wacky because Desmos isn't very good with the plus minus. And then for the plus, I have to restrict it to here, to 3. To get Desmos to draw the exact same thing. Bit weird. That's just because Desmos can't handle. Oh, and I still didn't get it. 9, sorry, 9. Just because Desmos can't handle the restrictions. There we go. So it's all of the negative, which I should have also figured out, and a little bit of the positive. But all you have to do is put plus minus in front, and then put the domain restriction, which will be the same as the range restriction up there. And that will limit your graph as well. Hope that made sense. I think I got to take a break here. Yeah, we've got a lot to go through. Maybe we'll do one more. Number 10, the height of a ball. Get a lot of ball throwing examples and a lot of profit margin ones. So height of balls thrown from balcony. Notice it's a negative leading coefficient. So it's going to face down. And height off the ground. Notice that it starts when t is 0. Just wipe those out, so it starts 35 meters off the ground. So if you're going to draw an x in the y-axis, note that it starts right up here. Most likely goes up. That's how most of the ball ones go. But I can tell from the standard that the y-intercept is 0,35. I can also figure out the x-intercept is going to be negative 10 over 2a, which is negative 10. So 1 is going to be the max height. We reach 1 comma something. Looks like minus 5 plus 10, 5. It looks like 1 comma 40. It's going to be the vertex. And I figured that out by doing minus b over 2a. And then plugging the 1 into the formula quickly. And you could always set height to equal to 0. But let's read the question. Write this in vertex format. So they want us to complete the square. Move the 35 aside. Factor out 5 from both of these. Minus 5 actually, because you want the t squared to be a positive. You're left with t squared minus 2t. And it will be t squared, not 2t2. And we're just going to leave the plus 35 over here. So it's going to be like that. I know that the perfect square of that, and now I have to create a big giant bracket, is t minus 1 squared. And I also know the square that's produced is minus 1, close big bracket. To get it out, I have to multiply that by minus 5. So to get it out of the big old square bracket, when I multiply it out of minus 5, it becomes plus 5 and plus 35, and there you go. It's plus 40. And as suspected, that's the vertex. So there's the vertex format right there. You can see that the peak of the ball is going to be 1, 40. Determine the domain. Well, in ball questions, you don't go back in time and you don't go down through the ground. So they have both a domain and a range restriction. So the domain along the x-axis, we need to figure out where it hits the ground. So that means we need to set this, I'm just going to clear this out, to equal to 0, or to the other one. But this one is a good one. Or we could have factored out, we could have found the factored form of this. And actually looking at it, the factored form isn't too bad because minus 5 comes out. You get t squared minus 2t minus 7. And I can see that it's going to be, let me just make sure, minus 7. Minus 5 minus 7. Which should be 7 and 1. But it's not. So we're going to have to do it the old-fashioned way. So we're going to set this this to equal to 0. Subtract 35 from both sides. So it's going to be equal to minus 35. Divide it by 5 on both sides. We're going to equal to plus 7. And by the way, that's not this. It's this. It should be this. Sorry. Yeah, so I used the wrong formula. So let's use the right formula. When I move 40 to the other side, it's minus 40. And when I divide by minus 5, it's plus 8. So you get this. Yeah, it's not going to be perfect. So you couldn't find the square. When I take the square root of it, indeed, it's t minus 1 is equal to plus minus square root of 8. We'll keep it for now in case it's something interesting. But I know it's just going to be the plus. And then I add 1. So that means that it's going to hit the x-intercept at t is equal to 1 minus the square root of 8. And t is equal to 1 plus the square root of 8. And if I look at in my calculator, 1 minus the square root of 8 is going to be the negative world that doesn't exist. And if I look at my calculator, 1 plus the square root of 8 is going to be the positive world. So if I'm going to put the domain and range restrictions now, I can tell you, well, it's not going to go higher than 40 on height. So it's going to be, the range is going to be YER. But it's going to be 0 is smaller or equal to y is smaller or equal to 40, the maximum height, and it can't go beneath the ground. And the domain is going to be 0 because you can't have negative time is equal to the time. And by the way, you should call this the height, h of x. And it's going to be smaller than equals to 1 plus the square root of 8 if I'm going to be really accurate. Because you'll discover that decimals are not accurate. But there's the actual decimal, but your teacher would want you to be exact. So that's the domain and range. Determine the model that describes the time in terms of the height. Okay, so this is the model that describes height based on the time. The model that's time based on the height would be the inverse. And very quickly, I'm going to let you know that it is. So if this is the correct formula, which I didn't keep a good copy of, so it's going to be minus 1 squared. And it's going to be plus 40. That means if I do find out the inverse, and it's no longer t squared in there, it's just the squares outside. If I do the inverse of that and swap my height and my time, it's going to be my new inverse, or yeah, if I do h minus 1 of t, is going to be t minus 40 times, or divided by minus 5, so it's going to be minus 1 in front. Let's see if I can do better writing than that. So I'm going to subtract 40 from both sides. Then I'm going to divide both sides by -5 if you want, but you don't ever keep a minus down here. So it's really 1/5 times that. And it's a negative, and then you're going to take a square root, and then you're going to add 1. And that would be the inverse of it. However, keep in mind, we now have to put proper domain and restrictions on that in order to get the proper inverse, which means the domain of this has to now be t0 must be smaller or equal to t, which must be smaller or equal to 1 plus the square root of 8. And the other one for the range of this, of the inverse, this is of the inverse now, the range is the same as the domain of the other one. Oh, this is the domain, sorry. Which means the domain of the original is the same as the range of the other one, which is 0 is smaller or equal to h of t, h minus 1 of t, which is smaller or equal to 40. So their domain and their ranges always swap. So just to show you on a graph, here's the original function. Just to make sure I get it right. That's plus 10t. There it is. And you can see that's when it hits the ground. Now here's the inverse. And yeah, it doesn't accept inverses, so we have to do it like this. There you go. It doesn't accept t's in inverses. However, to do it properly, I have to put the domain restriction here. And, oh yeah, I've got to put it for t. And there, that models the height properly. And if I want to do this one properly, if I want to do this one as the inverse, as I said, would be square root of minus 1/5 times x minus 40, all plus 1. So this would be the inverse. And I also have to put both down, one with the negative. And then I would then put the range restriction as the domain of the last one. Smaller or equal to x, smaller or equal to 40 for both of them. And that will restrict the drawing properly. There we go. Did it do it? Oh yeah. Now I have to put a range restriction on this one, because otherwise it'll draw it. So really, I've got to describe it as the range restriction that I did here instead. And I've got to put it as y. And I've got to do it again down here. I've got to put it as y. And I must put a y in the front, otherwise it won't recognize what I'm drawing. And does it still do it properly? I don't know if it did it properly. Yeah, finally did it properly. And the reason I had to put a range restriction here instead of domain is because it would draw the domain where it shouldn't, down below. Because the domain exists down there. Whereas really I want to restrict it. This one gets restricted based on the domain, so this one must be restricted based on the range. That's easier to understand. We take a little break. Okay, to continue, I believe we're on question 11. So we'll just focus on that. I hope we are. I think I did 10. So it's just another question about a ball being hit. And I prefer making a t-table, or t-chart, I guess, in which that is vertical. Now, time is often the same as x. It's always going to be the independent because time marches forward independently. Now, we can actually skip every 0.5 if we want, because it won't accurately reflect a per unit change. So I'm just going to write a notice at height 0. So this is someone striking a ball from the ground. So it starts at 0, 0, which means time 0, height 0, which helps a lot in determining the curve. However, I would strongly suggest skipping every second value and focusing on the ones that go up by 1. Yeah, we can find out the differences every 0.5, but we'd have to multiply those differences by 2 to get an idea of what's going on. However, we'll do it both ways. So what we're going to do is find first differences. How much did that go up? It went up point plus 12.375. How much did the next one go up? It only went up 10 point, it looks like 125. How much did the next one go up? It looks like it's going up less. So we can see sort of a gravity taking place. The subtractions get harder, which is why I suggested doing one every one instead. And it's roughly 7. It's actually 7.875. Yeah. So if I add that to 22.5, and the next one, it's clear it's only going up 5.625, and the next one, it's only going up 3.375. So we can see the ball's going up less and less. So we know that that's not a linear line because those numbers are not the same. If we do this one, we can see we have a negative, which would imply that this is going to be downward facing parabola. That went down 1. Oh boy, the subtraction's hard. 1 point. Oh no, it went down 2.25. And this next one went down, probably the same, let's say. Looks like it went down negative 2.25 again. I think that's it, yeah. And this next one looks like it went down negative 2.25 again. And same with this. Now all those numbers are the same. That means we're dealing with a quadratic, or something to the power of 2. This negative means it's going to be downward facing. And we can even figure out the formula. Let's use the first and second difference to extend the table. Okay, we did that. Graph the data. We could do that. Graph the inverse relationship. We could do that. Is the inverse a function? No. So if you have a parabola, and I'm thinking this thing's going to look like that, the inverse will be a sideways, and it is not a function. However, if you consider that the only part of this that matters is from the positive time and the positive height, then the sideways function, you might be able to argue that the domain of this will be from wherever it rises to wherever it lands, so 0 to wherever it lands. And you could argue that only half the parabola should exist based on whatever domain and range we find. Now the actual inverse of the formula, no, it's not going to be a function. But the inverse of the reality situation, it's probably also not going to be a function now that I look at it. It's going to be a sideways curve. So generally speaking, the inverse of any parabola is never going to be a function. If I'm going to do this on graph paper, it's fine, but be aware that you can also do it with a table on your Desmos, which will make things a little bit easier. Desmos also has a feature where it can figure out the formula for you. You have to put it in standard form. But as we can see, we can get a good idea of what this ball is doing. It's going to go up. It's going to reach a peak. And if we complete the square, we'll find that peak. But if you do this, so y1, which means I'm going to take the y values from the table above, is equal to a x1 squared plus bx1 plus c. And by the way, we can see that at 0 y at 0 values, why won't it? Doesn't make me put it after. We can see from the 0 values up above that there is no c because at 0, 0 goes through. So let's see, will it? Oh, I know why. I've got to put a little thing here. It's the shift, it's the tilde. And now it's going to tell me roughly what it feels A is and what it feels B is. So if we put this in, 5 squared x squared plus 27, not quite. And what did it give me for the R? Residuals plot. Oh, I forgot the x. There we go. We can see that this well does indeed fit. We can also see that it looks to be that the maximum height we're going to hit is there, and it looks like we're going to hit the ground at 6. So let's keep that in mind, but let's also just keep in mind that to plot the inverse, all I do is switch all those values. So over here for y, I'm going to do it like this. And for x, I'm just going to use the values I saw for y. And you'll see sort of an inverse. It's going to be coming up and then coming around again. And it's facing the other way because it's got a negative value. Now, Desmos can also calculate a formula from those second ones as well. So you can do shift tilde. And you just have to use the correct thing. So we've got a square root function of x2. Couldn't quite do it because we're missing a couple of values. We could do b, and we're not going to have a c here. And let's see if it's capable of doing it. No, it's saying that, and they're saying it's a b, just 1, and I can see that doesn't quite fit. So I mean, I could do a negative a, but that's still not going to fit. So it's easier if I look at my original values here, and I can see this. So this is the original function. And they're not asking for this, but I just want to show you how you do it. And I can see from this chart that when x is 0, y is 0, so there's no c. So that's the standard function. And I can see when I punch in 1 for x, I get 22.5 for y. So 1 squared times b times 1. So that means a plus b is equal to that, or b is equal to 22.5 minus a. When I do it again for when x is 2, I get this for y. 2 squared is 4. So you get this. Now I can replace where I see what b is equal to right here. Oh, sorry, this is there. There we go. Since b is equal to this up above in this bracket, I can just replace it with where I see b. So when I multiply that out, I get 36 is equal to 4a minus 2a plus 45. So that means 2a is equal to minus 9. Is that right? 36. Is that 36? Yeah, let's see. 4, yeah, minus 9 when the 45 goes the other side, which means a is equal to negative 9 over 2, which is equal to negative 4.5. And if a is equal to negative 4.5, then b is equal to 22.5 minus 4.5, which is plus 4.5, which is 27. So you can see we figured it out algebraically what this is equal to. So now I can take my formula, which I now have, like that. I can do several things. First of all, I can always take out x out of both, or minus 4.5x out of both, to determine where it hits the ground. So if I take 27 divided by negative 4.5, that's how I factor something out. I'm dividing it by it. I get the negative 6 that I anticipated that the graph already showed me, which means the ball starts off at the ground 0, 0 and hits the ground 6 seconds later, which means the vertex is 3. Now I can go and complete the square, or I can actually put the y value in for that vertex. What's 3 squared? It's 9. What's 3 times 27? It's 81. So you're going to discover that this is half of 9, so it's half of 81. So it's going to be negative half of 81 plus 81, which is going to be, what's half of 81? 20.5. So it's going to be 20.5, which means that I will have a vertex formula of like this. So that's one way to do it. Once I find the x value of the vertex, I can just plug it in. I could have also found the x value of vertex by taking negative b and dividing it by 2 times a, and I get a3 again, which tells me I had the right vertex, which I figured out right there. And finally, I can complete the square. So if I complete the square on the right, so I'm just going to push this a bit, and push the whole thing to the right and left a bit. So if I complete the square, I get minus 4.5, and just leave the x in there. So we'll do it properly here, because my writing's not very good. I'm left with x squared minus 6x like that. When I complete the square, I know I'm going to be dealing with x minus 3 squared. The square of minus 3 is 9, so it's minus 9. But all of that's going to be inside a bracket like that, which means to get that minus 9 out, I have to multiply it by 4.5, negative, times minus 9 will become a positive, plus 40.5. Oh, looks like I did a mistake down here. Oh, I did half of 81 and said 20.5. Yeah, half of 81 is 40.5. Sorry. You probably caught that. I should have caught that based on the graph of the numbers in the thing. But we see that completing the square also gave me the information just a little bit longer. Now also notice that I discovered the x value of the vertex there, and I could have simply substituted it in to discover this number. That's called partially completing the square, instead of figuring out all this multiplication. So that's completing the square. And if I was to do the inverse, now notice it has domain restrictions and range restrictions. The domain is 0 is smaller or equal to the time, which is smaller or equal to 6, and 0 is smaller or equal to the height, which is smaller or equal to the maximum of the height, which is that. Which means when I flip it, the new one will have an x restriction of this, and the y value will have they'll essentially swap their domain and range. If I'm going to resolve this here, I'm going to let you know that the inverse is equal to this. So f of inverse is going to be equal to the square root, and it's all going to be plus 3 on the outside, and it's going to be x minus 40.5 all over, so it's going to be a minus in front, all over 4.5, and then plus 3. So essentially I put that in there. I put that as a divider. I took the minus and moved it to the top. I square rooted it, and then I added 3. And if I put this into the formula up here, was it plus 3? Yeah. And there we go. There's the restriction. Now, that is just one side of it. I had to add a plus minus. So this is the other side of it. We can see the domain. I've got to put the domain restriction on there the whole time. And actually, I think because it's sideways, yeah, I can do it, I think. And I've got to put it on both, I believe. So that it's staying above 0 for and below 40.5 for x, and 0 to 6 for y. So you can see the inverse is not a parabola. It's not a function, rather. And then if I put the original back, I'm going to have this. And there we go. And just have to put the restrictions on the there we go. And that's the original one. Matches the dots. You can see all this stuff is discoverable and well worth learning. Okay, there's 12. This time I'll just answer the questions on hand, because I'm sure while some of you find it interesting, many of you just want to answer the questions at hand. And remember, this isn't a cheating video. This is for you to stop the video and see if you can do it yourself. Because if you can't do it on a test, there's no point in doing this. So to determine the vertex, we would have to either have to complete the square, which is what they want you to do, but just to make sure I get the right vertex, I'm going to use this formula. So it's going to be minus 3 over minus 6, so that it's going to be, the x value is going to be a half. And if I plug that in, I get minus 2 times a quarter, I get minus a quarter, plus 3 halves, minus 1. Just to multiply by 2 and 3. So we're going to minus 2 over 6, plus 9 over 6, it's going to be plus 7 over 6, plus minus 1. It's going to be a 6, I think. A half, comma, a 6. So clearly the challenge here is going to be completing the square, but we'll do it the standard way. They also want us to graph the inverse, but only for a certain domain. So I'm going to take the minus 2 out and get x squared plus 3x. And we're going to leave the minus 1 way over here. I know that the completion of that will be, it's going to be minus 3x once I take minus 2 out. Will be minus 3 over 2 squared. And this will create a 9 over 4 in a bracket. Did I get the wrong? Minus b over 2a. Yeah, that should have been 4. So I got that wrong. So it should have been 3/4. Oh, and also I factored that out. I did all this wrong. So when I take this out, good thing I kind of did the b thing. What's left in there is x squared minus 3 over 2, which is what happens when I factor that out. Leave the minus 1 over there. So this is what happens when I factor out the 2. And then if you ever want to find the half of a fraction, just double the denominator. So that will, there we go, and that's the minus 2 over b, which I also did incorrectly. And I also know that the minus of that will be minus 9 over 16, which I have to put in brackets like that. And then it's all going to be minus 1. And then to get that outside the brackets, I have to multiply by minus 2. So I get x minus 3/4 squared. When that's multiplied by minus 2, the 16 becomes an 8. So I get plus 9 over 8 minus 1. And I even got the y value wrong because I had that wrong. And 9 over 8 minus 1, which is 1 1/8, becomes plus 1/8. So that is the formula for that. If I'm going to graph it, yeah, I could very quickly. The vertex is going to be at 3 1/4, 3/4 rather than 1/8, so it's really tiny. It's going to be facing downwards. Let's see, it's going to be 3 1/4. It's going to be like way close to the x-axis. It's going to go through 0, minus 1, so there's another point I can use. It's going to be very tight to figure out the x value, so it's easier to take like a minus 3 down here and figure out a couple points that way. So minus 3 would be 9, minus 18, minus 9, so minus 18, minus 9, minus 27, minus 28. So you get minus 3, minus 28. And what else can we do? Yeah, probably minus 1 would have been better. Let's use minus 1 and 1. So minus 1, and actually I should do on the equal side of the vertex. That's okay. Yeah, I'll just do minus 1. So it's minus 2, minus 3, minus 1. So it's minus 1, minus 6. And when I do, let's say 2, I get 4 minus 8 plus 6. So minus 2, minus 3. So I get 2, minus 3, which is a little bit higher. So I probably should have used the 3. Let's try a 3. 3 is 9 minus 18 plus 9 minus 9 minus 1 minus 10. So I get a 2 minus 10. So that's even lower. So I don't have some nice even points here, which is kind of annoying. However, I can still graph it, just finding some points like that, taking random points. Now, if I'm going to graph the inverse, then this is going to switch spots. It's downward facing, so it's going to go this way. Normally it would go that way. It's going to be at 1/8 x, 3/4 y, and it's going to go like that, and it's going to go through the point minus 1, 0. So there, like that. And I'd have to take a couple of these points and just swap them. Domain and range, so they're asking me to find for when y is smaller than 0.75. So they're asking me to go from the vertex downwards. So they've already given me the range. Oh, for when x is bigger than 0.75, and the vertex of the inverse will be this. So the range is going to be y is bigger, equal to minus 0.5, but the domain is going to be x is smaller or equal to 1/8. That value. Were the values of x restricted in part C and D? Determine the... Oh, so this one, they want me to graph it just for this. Then they want me to determine the range. And then they said, why are the values of x restricted? Okay, probably to create a function. So let's put all this into Desmos and see if that's what we get. I'm going to erase all the old stuff here. And we're going to put in the original function. We're going to put in our completed the square function. And if I want to do a quick inverse, so there it is. Notice that they're the same graph, so I got it right in the completing the square. I probably could have figured out those values by factoring because they look pretty even. I probably should have. And then if I want to do a quick inversion, I can just do this, and instead of y put x, and instead of x I can put y. And then notice they asked me to restrict the y here for only bigger or equal to 0.75. And that's to create a function essentially, because they've restricted me from its vertex. By restricting that, I've restricted the x values possible as well. So essentially created a function by restricting that. If I don't restrict it, the inverse looks like that. And the equation of the inverse very quickly is this. Square root minus x minus an eighth, all divided by 2, outside the brackets, plus 3/4. There we go. So there we go. There's the inverse, and here's the blue line. So you can see that I got it right. And the reason I don't have the other half is because I also have to add a version that's a minus. Like that. Make it green as well. So if I turn off my green, I can see I'm right on the blue, which means this is indeed the correct inverse. Now it would also often be written like this, instead of divided by 2 like this. And it's going to be the same thing, but it can make the transformations a lot more obvious. Hope that was helpful. Moving on. Each graph shows an f that has a parabola and a bunch or a branch of a parabola. Determine f of x, graph f minus 1, state restrictions. I don't know if I'm going to do each of them, but I will show you how to do it. And it's very much like what we've been doing. So the secret first is to find some very clear points. So I'll just take all of that. And if I look at this one, for instance, it's a downward facing parabola, right? So a is going to be negative. The leading coefficient is going to be negative. But I can see the vertex is right there, 4, 1. And you should probably label that. Which means I know that this formula is going to be this. I just don't know a. But I can see some very clear points for the x-intercepts at 5, 0 and 3, 0. And either will be good. I'm going to use 5, 0. And that means y is 0 when x is 5. 5 minus 4, 1. 1 squared, 1 plus 1, which means a is equal to minus 1. So now I can put this back. Wherever I see a, I can just put this number. And I have the formula. Didn't take that long. Determine f of x, graph the reverse. Okay, so they just want me to graph. So swap these numbers, 4, 1, 1, 4, right there. This one's 3, 0, so 0, 3. This one's 5, 0, so 0, 5, which is off the graph. It's just kind of there. And a lot of it's off the graph, but it's going to look like this. Like that. and it's going to have reverse domain. So it's going to be 1 comma 4, and it's going to be x is smaller or equal to 1. Whereas this one, it has a range restriction of y is smaller or equal to 1. State the restrictions on domain and range of the inverse function. Okay. We just did it. And I guess, are we supposed to do a half? No. To make the inverse of a function or to make it a function? Now, and then they want us to do the equations for that. Now, I can tell you that all I have to do is switch all of this up. So it's going to be f of x. It's going to be a square root. It's going to be x minus 1. It's all going to be divided by minus 1, so it's just going to have a minus in front. That's what's going to be in the square root. And then plus 4 is going to be out the outside. So this will be the function. So this goes inside as a divider, but that doesn't matter because it's 1, and this will go outside as a y-intercept. If you don't understand how I did that, just unravel this equation, swap their x's and the y's, and unravel the equation in reverse bedmass order until you get to y. Essentially moving from the outside in. And I've done it on lots of previous videos in this section. So there you go. And I've done the restrictions. They're all like that. Find a clean value. That's your best. Find some clean points. That's your best thing to do. First thing I'm going to notice is the vertex here is 1 comma minus 3. And I'm going to write it down. By writing things down, you're less likely to make mistakes. And as you've seen from all my videos, everybody is prone to making mistakes. However, I now know that this is the formula of the vertex. All I need is another clean point. And that one looks very clean there, so that's the y-intercept. And there's not a lot of other clean points, so I'm going to use that y-intercept, which means y is minus 2 when x is 0. So when x is 0, I get minus 1 squared, which is 1. So it's that. And which means I add 3 to both sides, and a is 1 or not existent. So really, this is the formula. And I can tell you that the inverse formula is going to be this. And it doesn't have any dividers, and then outside of it is going to be a plus 1. And I forgot both last time as well. That should say plus or minus. Whenever you take a square root, you got to add that plus or minus. So notice this became an x translation, and this became a y translation with the opposite actions. And if I plot the inverse, so just switch those around, minus 3 comma 1, it's going to be up here. This is upward facing, so it's going to go like that. And then minus 3 comma 1. And then I'm going to reverse this one. I'm going to do minus 2 comma 0. Like that. If I see a couple other clean points, I'll use them. That's a clean point. Fairly clean anyway. It looks like 3 comma 2. Oh, this is not 1. So I've got to make sure, always check your scale if this one's going up by 2's. So if I'm going to switch that, it's minus 3 comma 1 is actually there. And minus 2 comma 0 is actually there, which means there's going to be an identical spot there. Right there, yep. And any other clean spots? This one's clean. It's 3 comma 2, so 2 comma 3. Like there. And I can pretty much go like this now. That's the inverse, and you should label what you know as well. So you'd always label the vertex like that. And whatever other points. You should label all the points that you discover. This one, keep in mind, because it is a half a parabola, so it has a, oh, What are the domain and range restrictions here? So for blue line, it only has a range restriction. And for red line, it has a domain restriction. And they happen to be the same restrictions. Okay, so for this one has an it has a domain restriction in place. So you have to immediately notice, okay, well this is a parabola, but now they've given me some restrictions on the domain, which means x must be smaller or equal to -3, and y appears to be bigger and equal to -2. So the first thing you should do before you do the other stuff is know that the restrictions on the other one will be the flip. Their domains and ranges will flip. And that'll help you immediately. It'll also help you immediately once you realize that this is the vertex. And you'll immediately say, okay, well, -2, 3, -2, -3 is right over here. And also this is an upward facing, so this one's going to be like this. The only question will be, will you go up or will you go down? Well, because x must be bigger than -2, it's got to go that way, and x must be smaller than -3, we know immediately we're going to go down. So we're going to only have this bottom half to branch. And the best thing to do would just be to find one other clean point. Right there, that's -5, 3, so 3, -5 is right there. And another clean one in there, probably this one, -4, -1, so -1, -4 right there. Which means I have this nice drawing right there, and I just got to join their points. And you have that. Now, as for the equation of the first one, whoops. The equation of the first one's quite easily defined because I have the parabola formula, vertex formula, and I know that this would be how I would write it. All I have to do is find a clean point, which I believe I have one at -4, -1. What's -4 plus 3? It's 1. What's 1 squared? 1. So I get this. When I add 2, I get a is equal to 1 again. So that means there is no a, really. And that means the inverse function formula will be this. And I should be really writing it as f of x, by the way. Should really be writing it as this, where the -1 is up above, like this here. And you should also have a little x in there. And it's going to be equal to, let's see, x plus 2 square rooted, and then -3, like this. And then these restrictions. And finally, the same thing's going on with this. This has pre-existing domain and range, so it helps to notice it right away. Domain and range restrictions. And it helps if we just start with the vertex. We can see the vertex is 2, 3, which will immediately help me dot out the inverse vertex, which will be here at that's at 3, 2. And I can also should immediately note the domain restrictions of this, which are not this. It's x is smaller or equal to 2, and y is bigger or equal to 3. I might have gotten the original range restrictions wrong here. Looks like it's smaller or equal to -3. Anyway, doesn't matter. And y is bigger or equal to -2. And anyway, it doesn't matter. I've already, let's see, what did I have originally? Yeah, no, I had it right. So just in this case, it's going to be 2 and 3. Okay. Now that means I can immediately write my domain and range restrictions for my red line, for my inverse line, as x is going to be bigger or equal to 3, and y is going to be smaller or equal to 2. Which tells me that this is going to go down here, because it's got to go down below 2. I could even take a couple of clean points, like this one is 1, 4, which is going to be 4, 1, which means there's going to be another, would normally be another clean point over here. And that looks to be about 0, 5.5, so it'd be about like 5.5 here, and I'd have something like this. As far as the formula, you do the same thing we did before. This is the main graph, and to find A, so I'm missing the A here. I should have had the A in there. And to find the A, I have to find a clean point. It looks like 1, 4. So when y is 4, x is 1. 1 minus 2 is minus 1. Minus 1 squared is 1. So you get A plus 3. And again, we discover A is equal to 1. So they took it easy on us. Which means the inverse in red is going to be this. F inverse x is equal to, and we have to keep the downside, so minus square root of x minus 3, and that's going to be x minus, I gotta make it smaller, x minus 3 plus 2. And that will create, did I get that right? Yeah. You can see there's the vertex in it. And just to make sure that I got the minus right, because I should probably test it out with like one of the values, like this one here. I should put 4 in for x, so I get 4 minus 1, square root 1 minus 1, plus 2, 1. Yeah, that's the right answer, so it is indeed a minus. You could put it in a Desmos to make sure. But it's either got to be plus here or a minus, and I have a feeling minus will produce the bottom side of it. And that's it for 13. Easier than they looked. 14, 15, 16. Do I have time for this? Oh, I have time for 14 and 15. And then I might have to stop. So we're going to do crop, and we're going to grab 14 and 15. What must happen for the inverse of quadratic function to find all over roots also to be a function? You would have to restrict the range on either side of the vertex. So either above the vertex or below the vertex, so that you get half a line or half a line. But as soon as you get 2 lines like that, it fails the vertical line test. If you're given a quadratic function in standard form, explain how you determine the equation of its inverse. In standard form, Jesus, that's actually a damn good question. I think I'd have to complete the square, and then I'd have to inverse the process. If the domain of the quadratic function is xer, will its inverse be a function? No. So an answer to 15b, no. When all domains of the function on a quadratic exist, i.e. when it's xer, the inverse means yer, which means it will be a sideways u. and not pass the vertical line test. And we saw that when we had half of a domain or half of the parabola, it would the inverse would still be a function. But when it's both the parabola, it becomes a u, which violates the inverse. So if you have half of the domain restriction, you can create a function. But if it's the full domain, which is in this case, you will not create a function in the inverse. Those were relatively easy. Let's see what 16 says. Oh, God. Meat department. So they're looking at a maximizing price. Discovers she can sell this amount of meat, where that minus that, where X, she sells it at X dollars per kilogram. So the higher this price, the lower her profit goes, and this is a line. She pays her supplier this much per beef. So that's currently how much she pays her. Determine an algebraic expression for profit, where P is an expression of total profit in dollars per week. Okay, so profit is equal to money times unit, right? And she determines that M of X is how much she can sell. Right? That's how many kilograms she can sell. She also determined that she gets $321 per beef. She also told me that M of X, how much she sells, is going to be $1,400. Oh yeah. So that's money per kilogram that she sells at X dollars of kilogram, but she's buying it from her supplier for that much. So X is a random thing. So her profit is going to be not that. Her profit is going to be how much she sells and her profit goes up and down depending on how high her X goes. Anyway, that's how much she sells, rather. And that goes up and down depending on how much she sells it for. But she has to pay. She has to pay $3.21 times how much she sells in kilograms, right? Because how much she sells in kilograms is mx, how many kilograms she sells, and how much she pays in kilograms is also determined by mx. So you see this weird thing of the higher she prices this, the less she's going to make. There's going to be a max price here. Now, if mx is equal to that, and profit is equal to how much kilograms she sells minus how much she pays per kilogram, right? You can replace both of those as profit is equal to 1,400, 700 minus 340x, which is how many dollars she sells hers, minus 321 times 1,400, 700. See if I can do it on 2 lines here. Minus 3040x. So if I do this first part, that's fine. But if I multiply this second one out, this part here becomes this. I gotta make sure I wrote down right, yeah. And this part here becomes this. So I'm gonna just make sure I did that first part right. And then when I now 321 that, hang on. I think I got it wrong. So I'm gonna pause and think more about that one. Okay, I figured out the other one, but here's 17. 17 is relatively easy, and you'll notice it right away. This looks a lot like this. And this is clearly a parabola. Well, when we do an inverse, all we do is switch the x's and y's. And when we switch the x's and y's, this is what you'd get. Well, it's clear that this is the inverse of that. Therefore, graph the relationship. Well, I would normally complete the square, right? I'd have to put it in the right order. But let's just pretend it's written like that. The completion of the square would be x minus 2 squared minus 4 plus 4. So it's x minus 2. And it's quite clear that that's a perfect square, isn't it? The one up above. Which means this one here is the same thing. It's x is equal to y minus 2 squared. You might be confused about how to draw that. And you'd be correct. It's no different than the inverse of this one. Well, this one has a vertex of 2, 0. Therefore, this one, and it might be confusing because the y is there, will have a vertex of 0, 2. And it's going to be sideways like this. To prove this, it's much easier to pull up Desmos and write the perfect square. Like that, which I believe is the thing we had. And then simply swap the x and the y's. Now I'll put the original back so that you can see that they are simply the inverse of one another. Make this one red. So there's that point, there's that point. 4, 4 they share because if you swap them, it's the same point. Just as if I swap these, let's see, why are those the same? Oh, because it's going to come in on a different angle, just as that is, so they share the same 1, 1. But I can find any spot on this black line, let's say 5 here, 5, it looks like 5, 4 point, it's hard to see what it's going to be. 5, 4.236. And if I go down here to 4.236, or up here rather, on the black line, 236, I'm going to find the 5. Let's see. Where did I find that 5? Oh, they were finding it on the 5 line? Okay. So over here on the red line, I'm going to find it 4.26 up at the 5, the same value. So all the values, all the x, y values are swapped. It's easier to see in a clean one, 4, 0, 0, 4. They share this one because they're both 4, 4. And you could find some more clean values if you looked further up, like there. There is minus 1, 9, so I'm going to find 9, minus 1 right over here, somewhere in there. And sometimes this thing's finicky, you got to zoom right in. And I can see, there we go. Anyway, it's clear that this is just the inverse. So once you figure out this one, you can figure out that one. The domain and range, well, it's x or is bigger or equal to 0. And it's y-er. Determine the equation of the inverse. Well, we just did that. Is the inverse a function? Yes, the inverse is a function. This red line is the inverse, and the black line is the original function. And notice when we write it like this, where the x's and the y's are swapped, it's the actual double function. It will draw both sides because it's doing it from a y squared perspective instead of a y is equal perspective. Now, to go back to 16, which was much easier than I thought, and I made one key error on it. And the error I made was, if you look at m of x, that's how many kilograms she sells, and the amount she sells goes down based on the price. But to figure out her profit, you have to look at it this way. Now, they're using profit incorrectly. Revenue, well, actually, you know what? Profit, she's right. Profit is equal to revenue minus cost. Revenue is equal to the amount of kilograms you sell, which is m of x, times the price, which is x. So then when I replace m of x with the actual formula in the correct order, it won't really matter. This is what I have for how many kilograms I sell, and it goes down as the price goes up. Cost, she pays $3.21 per kilogram, but that's going to be depending on what price she sets for it. So again, it's 321 times 14,700 minus 3040x. So it all depends on what price she sets, which is determined in x here, which means profit is going to be, and we should expand this one first. So if we expand it, it's 14,700x minus 3040x squared, or put in other order, is like this. And don't forget the squared. And this one here, when I multiply the 321 times 1400, I'm just going to add that to that. It's a weird price that they've chosen because they've just made everything annoying. There we go. So we get that. Minus. That. Minus that x. And when I put them together, you get this. Minus, and this is an important distinction, it's minus cost. So you must put that whole thing in brackets, which means this minus is going to turn this minus, and it's going to turn this into a plus. So it's going to be minus this, and it's going to be plus this. Now, you'll notice they have some like terms here, so you have to add them together. And you get this, x. So finally, you get this as your profit. Hang on. X. So I just got to put it all together here. Minus 3040x squared plus, and then minus this. And like that. Okay, so now we have a profit equation. Find the equation for the inverse relation. Interpret its meaning. Well, if this is profit based on price, then if I inversed it, it would be which price should I set based on profit. So this is clearly a downward facing parabola where the max value will be price, comma, profit, which means the other one will be a sideways facing parabola, which will be profit, comma, price. In other words, the far most right profit will tell me the price, whereas this one, the highest profit I will be able to obtain is determined by the price. This one, the highest price I can charge, is determined by the profit. Really the same graph. And to find the inverse of the equation, I should really complete the square. And so I'm just going to separate that entirely. And I'm going to just see if 458.4 is easily divisible by 3040. And it's not really. So that's kind of a bummer. Which means, because you're not going to quite get it perfect. But if you're going to leave it as a fraction, it's going to be x squared minus roughly that. I'll just leave it as a decimal. It doesn't really matter. X, and then the number doesn't matter. So far that's the completion of the square for the profit. I'm just going to get rid of this one because it's the longer one. We'll keep both of these to make sure I completed the square properly. And I'm even going to input this whole one in there to see if I did the whole thing properly. But you're going to discover that this is minus 340, x minus half of that. So it's going to be 458.4 divided by 3040 and then divided by 2. We're just going to keep that around because the number that gets subtracted is that squared, which is that. And to get it out of the bracket, I have to multiply it by negative 3040. And of course it's going to become positive, so I'll just leave it as positive here. And so this comes out. And I can get rid of this. And that becomes a square. And now I just have to subtract that. Which means that's my max price right there. Now, keep in mind that the price is in dollars, so I can charge, wow, that seems high. My max price I can charge is $2,008. It seems wrong. Could be that they didn't do the revenue correctly. And you know what? Looking at it now, yeah, profit should be revenue minus cost. Find an expression, fine. 1900 profit. Yeah, so that's the max profit, sorry, and that's the max price per kilogram right there. So I can charge $4.02, and the most I'm going to make is $2,008 in a week. And it's function to represent the price that will yield. Okay. Weird. Determine the price that will maximize profit. We just did. The supply cost drops to 310. What price should the manager set? Ugh. I'm going to let Desmos do that. So you can see the inverse process for this. This is squared, by the way. Will be the same. But first I want to see if I did all the processes correctly. And I'm going to use all the equations on the right. So I'm going to set my price, my revenue. I'm going to call it R. I'm going to call R 14,700 minus 3040x times x. That way I have it exactly as is. I'm going to set my cost C at 321 times 14,700 minus 3040x, which is that. And I'm going to call my P R minus C. And my green graph is what I'm going to look for, and I'm going to set my green graph to a maximum of, I think I said 2,000 was the profit, so I should see green somewhere in there. Yeah, I didn't quite do that. 2,000 should be the profit. That'll do it. Oh, I must have done something wrong. So, looking back at my calculations, right there. Just a typo. And that's good there. So looking at this, yeah, we're going to see green down there. There we go. And let's see if I got it right. Yep. Yep, there's my price, 402. And I got 4.023, but really we're rounding up to cents, so it's $4 and whatever. And that's going to be the max price, $2,008.17. Max profit. So I got that right, which means I not only expanded it correctly, but I completed the square correctly. So there's no need for me to check the completed square because these are the raw data, and I let Desmos do it for me. Now, in terms of an expression C gets changed dramatically. So if I'm going to pretend the price is the same, I would keep the same equation I just came up with, this one, and let's just pretend the price is going to stay the same, and I would show that the profit is 1,900, then this is just going to change to 1,900. And the square's there. So that's how that works. And by the way, the inverse would be this. So it would be, instead of profit, revenue based on price, it would be price based on profit. Price of meat based on profit. It would be the square root of x minus 2008. I'm just going to round it up to the penny. And it's going to have a minus in front. And it's all going to be divided by 30/40. That's going to be squared. And then outside is going to be plus 402 because we're dealing with pennies. And this whole thing is going to be square rooted like that. And since it's going to be a sideways thing like that or like that, we would put a plus minus in front. And keep in mind it's a fraction like that. And the minus is in front of the whole bracket like that. There. And that's the inverse. What if we change the price to 310? We'll do that right in Desmos. There's 310. That should, since it's a lower cost, that should raise my profit. That didn't help. Let's try making x 1 to 3. See if that helped. There it is. Yeah, so that raised my profit to $2,289.16 per week, and it means I could set the price of my beef at $3.98. Going back to what it was, which was $3.21. There we go. I'm going to look at how much my costs were. Woo! Costs are a straight line. So that's right, this is a straight line. Revenue, in red, should be a parabola. There's the peak of it. So that means I'm making actually a lot in the week, but my costs go up as my sales go up. So the more I sell, the higher my cost. So when you combine those two things, when you're subtracting this parabola minus that line, you get that little green line, which is that one. The more you study things, the easier they get. There we go.